Welcome to a video on section 3.6, the chain rule. I want to go over some of the derivative shortcuts from previous section just to remind you. We have the derivative of a constant is 0. The derivative of a linear function is just equal to its slope. When we have a power function, we can use the power rule, which is bring the power down as a multiplier, reduce it by 1. Remember, when we have individual terms, we can take the derivative separately. If there is a constant as a multiplier, it remains out front as you just take the derivative. There is a product rule, f prime g plus fg prime. I'll be using that in the video today. And the quotient rule, I believe I'll be using that as well. F prime g minus fg prime over g squared, as well as the trig functions, which are needed to be committed to memory as well, all those derivative rules. So what we're going to do in this section, in 3.6, is study the derivative of the composition of two or more functions. So let's remind ourselves what that is in the first place. So here's a little bit of a picture, and then I'm going to have a discussion of this. If you have two functions f and g, the composition of f of x and g of x is denoted by f compose g of x, is the way we pronounce that. And another way to read that is the alternate version is f of g of x. And so the figure below can show you what I mean by that. So if you were to put an x in at the left, that's your input over here. The first thing, if you're using this notation here, you would take the x and put it into the g function and get an output value, right? So the input goes in here. There's an output that comes out of this, but that output falls directly into the f function. So you take the output of the g function, put it in the f function, and that's an output. A composition of the function is a way to go all the way from left to right in one jump. So composing those two functions. I have a little note here. The order of the function is an important thing when dealing with the composition of functions, since f compose g of x is not equal necessarily. It can be, but it's not necessarily equal to g compose f of x. Most of the time they are not equal. In rare exceptions they are. Well, let's take a look at an example. If f of x is x squared plus 3 and g of x is square root x minus 2, find the following. So let's take a look at A, which is f compose g of 9. Let's remember our alternative way to read this. That's f of g of 9. So what it's asking us to do is first plug 9 into the g function. I have a graphic off to the right you can look at. We're going to have g as an input, 9 as an input into g. So we're going to put it into this function here. And you might be able to do that in your head, but I'll write it down. Square root 9 minus 2. That would be 3 minus 2. The output would be 1. And so what would fall out of this function is the value of 1. But 1 will then automatically fall into the f function. In other words, g of 9 is 1. But we still would have 1 then fall into the f function. So we have 1 squared plus 3. Evaluate that. Out the other side comes 4. And so that's how you do that. You don't have to draw the machines, but that's just what's going on. Let's take a look at B here as well. What is f of g of 1? Well, that's just f after you've plugged 1 into the g function. So now we'll just look maybe up at the function. What is g of 1? If you put 1 into that g function right there, square root of 1 minus 2 is negative 1. And so, get my pen back on. That'll be f of negative 1. And then you take the negative 1 and plug it into the f function on the left. That would be negative 1 squared plus 3, which is equal to 4. So same answer with a different input. Let's look at the reverse of that to see that it's not always true that f of g of 1 is the same as g of f of 1, or g compose f of 1. So this one will be first plugging 1 into the f function and getting an answer. So if we plug it into this function first, we'll get 1 squared plus 3. That'll actually be 4 for the f of 1. And then turn around and plug 4 into the g function. Square root of 4 minus 2 would be 0. And so you can see that, of course, these two are not equal, right? Not equal there, and that's often the case. On the right-hand side, we have f of g of x and g of f of x. This is where you're not plugging in a particular input value. You're plugging in any x to see what happens. So what would happen if we first look at any x value and plug it into g, and then take that and plug it into f? What in essence happens is you just get g of x itself, right? G of x with no particular input is just square root x minus 2. So you just replace the g of x with square root x minus 2, the function. And then that becomes an input. That becomes an input into the f function. So we'll look over here at our f function, right? It's x squared plus 3. So it's going to be equal to x squared plus 3, but our input is what I have highlighted in blue there, right? Highlighted in blue is the square root x minus 2. And so that becomes our f composed g of x. Now, I could distribute and maybe make that look a little bit different, but for now I'm just going to leave it. Let's look at the reverse of that, g of f of x. That would be saying put the f function into the g function. Okay, so the f function itself, like this, will be replaced by the actual function itself, which is x squared plus 3. And then x squared plus 3 becomes an input into the g function. So you write down the g function, which is square root x minus 2, but instead of putting in x, I'm going to replace it with that. So you can see that this is not the same as that. That's the basic idea. Review of composition of functions. Let's look at the derivatives. All right, so here we're going to be talking about something called the chain rule. Very important. Not that hard to memorize, but you'll be working with several examples to figure out how it works. So it says, let f and g be functions. For all x in the domain of g, for which g is differentiable, and f is differentiable at g of x, that just means we can find the derivative. Then the derivative of the composition function, h of x, equals f composed g of x, or another word to say it is f of g of x, is as follows. In other words, here is our derivative. H prime of x, if we have this composition of functions, will be f prime g of x times g prime of x. Now that's kind of a mouthful, and maybe I can say that in another way, which would be to take the derivative of the outside function first, the secondary function, the f function first, right? Leave the g function alone, and then multiply by the derivative of the inside function, the g of x. And so, maybe I'll write that in words. It's the derivative of the outside function and I'm using the word outside, maybe you'll see as we go through it, leaving the inside alone, function alone, times the derivative of the inside function. Now you can memorize this formula that I have here, but it's also, with experience, you can kind of see how it works to kind of think of it in the language that I'm writing there. Another way to say it using Leibniz notation is y is a function of u and u is a function of x. Then dy dx equals dy du times du dx. You can think of these du's if there were units simplifying out, and you would see why that would be true. So let's take a look at an example here. So number 1, find the derivative of h of x equals quantity 2x cubed plus 2x minus 1 all to the 4th power. Perhaps you can see it, but the inside function would be this piece right here, the 2x cubed plus 2x minus 1. That's going to act as my g of x. I'll write that down in this particular case. All right, g of x will be 2x cubed plus 2x minus 1. And then all of that seems to be sitting inside, right? Inside something to the 4th power. So something to the 4th power is the outside function, which we will think of as the f of x. So the f of x, our outside function, is x to the 4th power. Now let's go back and think about that composition of functions before we proceed. And maybe you can see how, if you think about putting the g function, if you put this function and replace it in here for x on the f function, you can see how we will in fact get this over here, right? It becomes all of that to the 4th power. So we're going to use the definition. We're going to say, well, if this is h of x, then h prime of x is equal to f prime, leaving g of x alone, times g prime of x. So we need the derivatives of f and g. Let's go ahead and do that. We use the power rule for that. Let's start with f. F prime of x, using the power rule, is just 4x cubed. All right, g of x. We have separate terms. Let's use the power rule and the constant rule. This will be 6x squared plus 2. All right, so that is our derivatives for, I forgot to put my marking, but that's g prime of x. All right, so we have those. Now let's go ahead and fill it in over here off to the right, right? We want f prime g of x, so we want the derivative of f. The derivative of f is 4x cubed, right? But remember that g of x is inside it, so instead of 4x cubed, it's 4 blank cubed, and the blank is g of x, which is this inside piece. So it's 2x cubed plus 2x minus 1. I almost didn't leave myself enough room. And then, so that's the first piece, and then multiply it by g prime of x. That's nothing more than simply just writing the derivative of g of x, 6x squared plus 2. And that's my derivative. Maybe let's examine the pieces now so you can kind of see how this would work with the language that I have up here, right? So if you think of the outside function, it's a power function. So if you bring the power down, it becomes a 4, right? And reduce it by 1, so that's the outside function. And leave the inside alone, just leave it as it is. Then multiply by the derivative of what's inside. And so I was kind of wanting to speak this as you saw me do it. You can see that you don't have to take so many parts if you can really live this language here. All right, let's take a look at number 2. Find the derivative of j of x is all of this. And so, well, there's several ways you can think about it. I noticed that this is the reciprocal. And so I would rewrite this without taking the derivative first as negative 3 times quantity 3x squared plus 2 all to the 4th power. Now again, if you're to walk through the inside and the inside function you can see here is going to be that 3x squared plus 2. So that would be my g of x. And then my outside function, I know this is just a constant multiplier, negative 3, but my outside function is negative 3 something to the 4th power. So it's going to behave like this. F of x, the outside function, would be negative 3x to the 4th power. And perhaps you can see how if you inserted the g into the f function, how that would be equivalent to what we have off to the right. Oh, just noticed, maybe you guys already noticed in the video, and I apologize, I didn't write my negative 4 power. Yes, got to do that. That would kill it otherwise, right? So, yeah, that's the reciprocal rule. When we bring that up, it's a negative 4 power. Let's go ahead and do our derivative, f prime of x. We'll use the power rule. Bring the negative 4 times negative 3 is positive 12, reduced by 1. Negative 4 minus 1 is negative 5. So that's my derivative. Now, you could always rewrite it as 12 over x to the 5th, but I'm not going to do that right now. Let's go ahead and do g prime of x. G prime of x will be 6x. Great. Now, let's just walk through this. The derivative of j, using the chain rule, will be f prime of x. I'm using f and g, so it'll be f prime of g of x times g prime of x. And we have all the components we need off to the left here. So, let's see. F prime of g of x means take the derivative. It's over here. 12x to the negative 5, but don't write x. Instead, you're putting g in it, and g is the 3x squared plus 2. All right, and then multiply that by g prime of x. That's just my 6x right there. Now you can clean that up a little bit. I would likely combine 12 times 6x. That would give me 72x. And then since this piece has a negative 5th power, if I were to actually use this further in a problem, I would want to rewrite that as 3x squared plus 2 to the 5th power in the denominator using my reciprocal rule. Okay, let's try to do one without writing all the steps down, and maybe you can start to see a faster way to do this. This looks like the cosine function. I of x is cosine 5x squared, where the inside function is 5x squared. Now I'm going to take the derivative using just the language piece from above. I prime of x is the derivative of the outside function. The derivative of cosine, you might remember, is negative sine, but leave the inside alone. So again, chain rule, take the derivative of the outside, leave the inside alone, then multiply by the derivative of what's inside. The derivative of 5x squared is 10x. You always would want to write this in a little cleaner way, writing the 10x up front with a negative 10x sine 5x squared, and there's nothing more than that. That's your derivative using the chain rule. Let's try it again here with m of x. Maybe you can pause the video and try it yourself. Okay, maybe you tried that. So m prime of x, the derivative of the outside function, is cosecant. The derivative of cosecant is negative cosecant x cotangent x. But we're just going to leave that inside alone, right? Negative cosecant something cotangent of the same something. So we got that. That's the first part. Times the derivative of what's inside. The derivative of 5x is 5. The derivative of pi is a constant, is 0. It would also be cleaner to rewrite it with a 5 in front, so I might just rewrite it negative 5 cosecant 5x minus pi cotangent 5x minus pi. Okay, let's take a look at number 5. This one's a little bit different, but you need to recall from your trig course that when we write write or say sine cubed of x, what that really means is sine of x being cubed. It's a little deceptive, but in this case, the inside is sine, the outside function is the cubed. Okay, so maybe I'll go back and just do it as we did originally. Again, the inside function here in this case is sine of x, and the outside function is x cubed. You can probably see how that would work. So my derivatives are derivative of sine is cosine x, derivative of x cubed is 3x squared. So if we apply that here, our rule, right, we're going to, our chain rule, p prime of x is f prime, leave g alone, times g prime x. And again, you can do this without the definition once you learn the language itself. And so f prime of g of x, here's f prime over here, but we're going to put g inside of it. It's 3x squared. Okay, x, but again, we don't write x, we write g of x, times g prime of x cosine x, like that. And it's probably best to write it in the standard notation, which would be, we normally write sine x squared as sine squared x, like that, times cosine x. And that would be our derivative. All right, another way to go back and use the language as before, so I don't want to just like kill this problem, but if you want to get faster at it, you would take this piece up here and say something like, oh, so the derivative, the outside is 3, so bring the 3 down, reduce it by 1, and then multiply by the derivative of the inside cosine. So you can actually just kind of write it all down once you get used to it, but it takes a little bit of practice. All right, let's proceed on to the next page. Find the equation of a line tangent to the graph of k of x equals all of this, where x is -1. So now we're going to head and find that equation of the line. So we need two things. We need a point and a slope. Let's get that point first. We want the point where x is -1, so let's figure out what is k of -1. Maybe I'll pause the video, you pause it, and get it as well. Okay, so when I put in -1, I ended up getting a value of 1024, so that means it goes through the point -1, comma 1024. All right, next piece we need is the slope. The way we're going to get the slope is by looking at the derivative. So we need k prime of x. Now we're going to use the chain rule here because we are an inside function and the outside function is a fifth power. So applying the chain rule, take the derivative of the outside first, bring the 5 down, and reduce it by 1, but leave the inside alone. Just leave it alone. That's g of x. That's your inside piece. All right. But then don't forget to multiply by the derivative of what's inside. The derivative of 2x cubed, 6x squared, and then the derivative of 4x is 4. And the derivative of 2 is just 0 as a constant. So that is our derivative. But we want that value where k is -1. So we're going to plug -1 into that whole derivative. Again, I'll pause the video. You can try it as well. Okay, if I didn't make any mistakes, I have 2560. These are rather larger numbers, so got to be careful with those. Now let's find that equation of the line. Y minus y1 is equal to m times x minus x1. Our y value is given as 1024. We didn't make any mistakes. Our slope we found to be 2560. And our x value in question is -1. So x take away -1 is like x plus 1. If you want to write this in slope-intercept form, you would distribute 2560x, and then we got 2560 there. But we're going to be adding another 1024 using the calculator. I have 3584 on that, if I didn't make any mistakes. All right, now we're going to combine the chain rule with some other rules. Let's combine it with the product rule. Notice here we have a pretty complex looking situation. We have a function inside a fourth power. There's chain rule. And over here again we have a function inside the power rule, and then we're using the chain rule. And then to make matters better, some would say worse, but I say better, we're multiplying these together. So overall what's going on is we have a function times a function. That's the product rule right there. All right, so let's write down our product rule from a previous section to remind ourselves, right? We have, well, the product rule, f prime g plus f g prime, and what that meant for us is derivative of the first function times the second plus the first times the derivative of the second. So let's keep that in mind as we find q prime of x. So we're going to have really 4 parts here, right? So we have derivative of the first, derivative of this piece. Got to use the chain rule. So bring the 4 down, reduce it by 1, leave the inside alone. Got it? That's f prime of x, or f prime. That's the first part. Oh, I forgot. I'm going to use the chain rule. So bring the 4 down, reduce it by 1, but multiply by the derivative of what's inside. That would be -2x minus 5. That all is just the first part. and then times g, times the second function, just leave it alone. So times 2x plus 1 to the 12th power. Okay, great. We got this part of the product rule satisfied. Now plus fg prime. F is just the first function from the product rule, negative x squared minus 5x to the 4th power, times the derivative of the second function. I need to use the chain rule, right? So bring the 12 down, reduce it by 1, and then multiply by the derivative of what's inside. It's a 2. Now you could clean that up a little bit, make that a little bit better, but just for the sake of what I'm doing right now, I'm just going to leave it. Because we would use that, we'd have to be very careful plugging in anything. So let's apply the same idea here. I didn't have it as a heading, but you can probably tell I'm going to be using the quotient rule. Remember, that's f prime g minus fg prime over g squared, which means derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom function squared. So let's use that. Let's do that. Let's see, derivative of the top, sine x, will be cosine x times the bottom function, that's f prime, times the bottom function. So just times 6x, put the parentheses, 6x squared plus 4 to the 4th power, okay, minus just the top, sine x, times the derivative of the bottom, times the derivative of 6x squared plus 4 to the 4th. And I have to use the chain rule when I take the derivative of the bottom. So bring the 4 down, so it's times 4, and reduce the power by 1, leaving the inside alone, and then multiplied by the derivative of what's inside. That would be 12x, all over the bottom function, 6x squared plus 4 to the 4th power squared. Now we can clean this up quite a bit. Maybe I'll just write down just a little bit for you here just to show you what can be done with this. There's multiple things you can do with this to simplify this quite a bit. And so like if you were to ask, the computer, if you go online and look at a simplified answer, you would see that it looks much different than what we have here. So you have to use some kind of factoring techniques. You might notice that on the top, they both have a 6x squared plus 4 to the 3rd power. Actually, this one has a 4th power. This one at least has a 3rd power. So you could factor out 6x squared plus 4 to the 3rd power. All right. If you factor it out from the first term, you're left with cosine x times 6x squared plus 4. You have 1 left because there was 4. Minus, if you factor out from the second one, you're left with 12x and sine x times 4. So putting that all together, 12 and 4 is 48x. 48x times sine x, if I didn't miss anything there on that particular factoring. Okay, there we go. Over the bottom, when we have a power to power, we multiply. So it's 6x squared plus 4 to the 8th power. Now what you can do to simplify this further is notice that these 3 here would simplify with 3 of these and be left with 5. And that would be a cleaned up version. Still quite a bit of a mess, but that would be probably a better simplified version of that. All right, differentiating a composition of 3 functions. What if there's a function inside a function inside a function? Is the case here, and let me point that out. So you have x squared plus 2, that's the very inside function, sitting inside a power function, sitting inside a cube root function. There's a couple ways to handle this. One is just use the chain rule back to back, but we'll reserve that for the problem below. Well, actually, I don't really have to do that too much below, but a little bit below. For this one, what I'm going to show you is just a little algebraic technique. Remember that 3rd root means, another way to write that is 1/3 power. So we can think of this as x squared plus 2 squared to the 1/3 power, and then use the power to power rule to write it as x squared plus 2. 2 times 1/3 is just 2/3. Now when we take our derivative, we only have to use the chain rule once. Derivative of the outside function is just use the power rule. Bring the 2/3 down, leave the inside alone, reduce 2/3 by 1, we get negative 1/3, times the derivative of what's inside 2x. If you wrote this a little bit cleaner, you might notice that 2x times 2 could be written as 4x. On the bottom we have this 3, and then this negative can flip down, reciprocate to a 3rd root of x squared plus 2. And that would be a little bit cleaner answer. On number 10 here, this is going to be a double chain rule. Remember that 4th power, the best way to read this is cosine of 7x squared plus 1 to the 4th power. Double chain rule. There's a function, 7x squared plus 1, inside a function, cosine, inside a function, 4th power. Okay, so to do this, you just start with the outside, very outside piece. The very outside is the fourth power. So if we want t prime of x, we're going to use the power rule. Bring the power down, 4, and reduce it by 1. Now it's cosine, I'm just going to write it here, cubed of 7x squared plus 1, all right, times the derivative of what's inside. What's the derivative of cosine? It is, I'm going to put parentheses so I can put my negative sine of 7x squared plus 1, but there's a function inside that, times the derivative of 7x squared plus 1, 14x. All right, and I think I have the appropriate number of parentheses. If you want to write that a little bit neater, you could. You could combine like the 14 times the 4, and I believe you get 56, if that's correct. Yeah, 14 times 4 is 56. We have a negative sitting right there. Put a negative in front of it. We have an x. We'll put that in front, and then you can just put the sine and cosine. I usually put them sine first, but it doesn't really matter. 7x squared plus 1. And then you have cosine cubed of 7x squared plus 1. That's just a little bit cleaner version of the same answer. All right, number 11 here. Kind of scooted over, sorry about that. Number 11. H of x is f of g of x. This one is just using the chain rule itself. If we just write the chain rule, h prime of x is derivative of the outside, leave the inside alone, times g prime of x. Then all it is just a matter of just using the information right over here. All right, so let's figure it out. It says if g of 1 is 4, g prime of 1 is 3, f prime of 4 is 7, find h prime of 1. Oh, okay, so what we want to do is find h prime of 1. Let's do that. So h prime of 1 just means plug in 1 for x. So it's going to look something like this. Just put in a 1 everywhere. Now this piece, g prime of 1, that's given as 3. Okay, so that's nothing more than saying, oh, that's times 3. And piece here, g of 1, that's given up here as 4. G of 1 is 4. So I'm just going to replace the g of 1 with 4. And then notice now that it says f prime of 4, right? And that's given up here as 7. So I'm going to replace that with a 7. And so I would get 7 times 3 is 21. All right. Last page, number 12, let's use an alternative notation. That's the dy dx notation. So if we're given a function just y rather than f of x or s of t or anything like that, we're just going to write our derivative as dy, in this case dx because the variable is x, and let's use the chain rule. The chain rule is derivative of the outside function. Derivative of tangent is secant squared x. Let's leave the inside alone. 4x squared minus 3x plus 1 times the derivative of what's inside. That would be 8x minus 3. All right, good enough there. Last problem is having to do with displacement and so on. It says a mass hanging from a vertical spring is in simple harmonic motion, kind of moving up and down probably, as given by the following position function, where t is measured in seconds and s is in inches. All right, so remember those units. T is in seconds, s is in inches. Find the position or determine the position at t equals 1.5. Well, since this is the position function, we're just plugging in 1.5. So we're going to get negative 3 cosine of, we got 1.5 times pi. I'm going to write it as 1.5 pi plus pi over 4. Now, since our tests are without a calculator, we want to really think about what is this. The 1.5 is a decimal. We got the pi over 4 is a fraction. So I probably want to resolve that first. I want to figure out like what in the world is all of this right here. So I'm going to analyze this kind of off to the side. 1.5 pi plus pi over 4. Now 1.5 means 1.5. You probably are aware of that. 1.5. And 1.5 as a improper fraction, 2 times 1 plus 1 is 3 over 2. So maybe it's better to think of this as 3 pi over 2 plus pi over 4. Now we don't have a common denominator, but the least common denominator is 4, so I can multiply this one by 2 over 2, and that will give me 6 pi over 4 plus pi over 4 is 7 pi over 4. We're going to use that for the remainder of the problem. So we can go back over here and go, oh, it's just negative 3 cosine of 7 pi over 4. Now you might remember in your unit circle, right, with that location, if you have this unit circle. All right, let's see. You got pi over 4, going by those quarters, 1, 2, 3, 4, 5, 6, 7 would be this location right here. And you might remember the location of that point is over square root 2 over 2 down square root 2 over 2. Okay, and we are wanting the cosine value. Remember, the cosine value is just the x value of this coordinate. So it's going to be negative 3 times square root 2 over 2, best written as negative 3 square root 2 over 2. That's the position. So the spring would be in the downwards position at 1.5 seconds. If it's oscillating up and down, it's negative 3 root 2 over 2. Oh, I didn't put my units. Inches. I'll squeeze them in there. Inches. All right, let's take a look at B. Find the velocity. If we want the velocity, remember the velocity function is, oops, I wrote that wrong. Don't write that yet. The velocity function, v of t, is equal to the derivative of the position function. So we need to find the derivative of s of t. And looking back up to this function here, we have to use the chain rule. We have a function inside a function. The outside function is cosine. Remember, the derivative of cosine is negative sine. So it'll change the negative 3 to a positive 3 sine of leaving the inside alone. All right. Times the derivative of what's inside. The derivative of the piece inside. The derivative of pi t is pi. The derivative of pi over 4, that's a constant, is 0. So we just get 3 pi, I'm going to move the pi to the front, sine of pi over t, pi t, plus pi over 4. Now we want this at 1.5, so v of 1.5 would be equal to 3 pi sine. Now remember, we figured out what all of this mess is already when we plug in 1.5. It's 7 pi over 4. I'm just going to use my same analysis from before. I'm not going to rethink that every time. Okay, and so we have 3 pi times sine of 7 pi over 4. Sine is the y coordinate, which is negative root 2 over 2. And so we would write that as negative 3 pi root 2 over 2. And I believe that it's in inches per second is the velocity. All right. Last one is acceleration. Remember, the acceleration function is the second derivative of the position function, but that just means it's the derivative of the velocity function. So we don't have to go all the way back to s. We can just take the derivative of the velocity function. And remember, the velocity function was given up here. So let's take the derivative of that. So we have a of t is, we're going to figure out what is v prime of t. So 3 pi is a multiplier. The function is sine, so the derivative of sine is negative cosine. Leave the inside function alone, and then multiply by the derivative of what's inside. What's inside is just pi. So if we simplify this, notice we have 2 pi's here. So we have negative 3 pi squared cosine of pi t plus pi over 4. And now we're going to evaluate that at t is 1.5. So a of 1.5 is negative 3 pi squared, and we already figured out this from before. Remember, you can even scroll up and look at it, right? We figured out from before that cosine of 7 pi over 2 was root 2 over 2, just kind of going back and forth between cosine and sine. So that would be a root 2 over 2, and simplifying that, negative 3 pi squared root 2 over 2. That's some kind of crazy looking thing, but it is just a decimal if we were to use a calculator. And the units are, what are we in? Inches per second squared. That's our acceleration factor. All right, that's all for this video.